All right, class, continuing our notes on types of bonds. When we're comparing physical properties like boiling point or melting point or hardness, malleability, brittleness, there's a lot of different types of physical properties. We need to compare the attractive forces between the units because we're talking about a physical property. Nothing's really changing. When we're comparing chemical properties, so that was physical, okay? When we're comparing chemical properties like combustibility, reactivity, non-reactivity, we need to compare the attractive forces within the units, so within molecules, formula units, and so on, within the particle. For physical properties of ionic compounds, you need to consider the strength of ionic bonds, because there are ionic bonds holding the units together. So even for physical properties, we need to consider the strength of the ionic bond if it's an ionic compound. For chemical properties of ionic compounds, you need to consider the strength of your ionic bonds. It's the same thing whether we're trying to melt it or whether we're trying to do a chemical reaction. You're still dealing with the strength of the ionic bonds, whether we're talking about a physical property or a chemical property. For physical properties of metals, you need to consider the strength of the metallic bonds. For chemical properties of metals, consider the strength of the metallic bonds. Now this sounds very repetitive, but it gets a little different here. For physical properties of molecular compounds, we need to consider the strength not of the bond, but of intermolecular forces. Whereas for chemical properties, not physical, for chemical properties of molecular compounds, you need to think about the strength of covalent bonds. So you see, it's very important to know whether we're talking about a molecular compound or an ionic compound. And we'll do some practice with that. Now we talk about changes. When matter goes through a physical change, like tearing, crushing, melting, sticking, freezing, the attractive forces between the units are either being broken or formed. The substance doesn't change, it's just going through a physical change. When matter goes through a chemical change, such as burning, oxidizing, decomposing, or combusting, the attractive forces within the unit, not just between the units, but the actual bonds within the unit are being broken or formed. So chemical bonds are being broken or formed. That means that the substance changes. It becomes something different. When an ionic compound goes through a physical change, ionic bonds are either broken and or formed. When an ionic compound goes through a chemical change, ionic bonds are either broken and or formed. So if we're doing a physical or chemical change, if it's an ionic compound, you've got to do something. You've got to either break or form ionic bonds. That takes quite a bit of energy. When a molecular compound goes through a physical change, IMFs are either broken and or formed. But when a molecular compound goes through a chemical change, then covalent bonds are either broken and or formed. I want you to make note of this. This is the one that's a little different. So this is really important to remember. It's harder, it's easier to do a physical change with a covalent compound than with an ionic compound, because you're only having to change the intermolecular forces, which are easier to break or form. So when a metal goes through physical or chemical change, metallic bonds are either broken and or formed. And when a metal goes through a chemical change, again, metallic bonds are either broken and or formed. So ionic and metallic have some similarities in this unit in the way we think about them. They're a lot more challenging to change than a molecular compound if we're talking about a physical change. Generally, the strength of a chemical bond, whether it's ionic, covalent, or metallic, a chemical bond is greater than the strength of intermolecular forces. Be aware of that. We got an example question here. Glucose, C6H12O6, melts at 146 degrees Celsius. While table salt, so that was glucose, it's a covalent compound, and table salt, NaCl, melts at 801 degrees Celsius. It says to explain the difference of the melting point of these two substances. So why is it that it takes so much more heat to melt table salt? See if you can answer it, and let's walk through it together. Pause the video if you need to. Glucose is a covalent compound. So molecules are held together by IMFs. NaCl, table salt, is an ionic compound. Okay, this one's a covalent compound. This is an ionic compound. So ions are held together by ionic bonds. Which one's easier to break? Breaking an ionic bond takes more energy than breaking IMFs because IMFs are easier to break. Now I will mention down here I've got some pictures. This isn't actually glucose, but it's a very similar concept, and it's a simplified picture. You can see that we're just breaking intermolecular forces if I wanted to separate one molecule. But if I wanted to separate a formula unit of NaCl, I've got to break it apart from all of those other NaCl formula units in the lattice. So I'm still breaking IMF, or I'm still breaking ionic bonds, even if we're just doing a physical change. And breaking an ionic bond takes more energy than breaking IMFs. So the melting point of NaCl is larger than the melting point of glucose, which means it's harder to melt it. You've got to raise it to a higher temperature. It takes more energy. Electronegativity and bond polarity. Electronegativity is a measure of the tendency of an atom to attract shared electrons towards itself in a bond. We've talked about this in the periodic trend notes. You remember that group 1A is the least electronegative group because it's over here. Remember, electronegativity, the least electronegative element is francium, and the most electronegative element is fluorine, so we would say that electronegativity really increases going this way. If you wanted to draw that on your periodic table, I'm going to go ahead and clear the ink on this slide. And then group 7A is the most electronegative group. Bond polarity is a measure of how equally or unequally the electrons in a bond are shared. So that means if there's one that is very electronegative and the other one is not at all electronegative, that's going to be a pretty polar bond because one of the atoms is going to be pulling the electrons to itself with much greater strength than the other one. We got an example here. So we want to give some examples of each of the following bond types. Start with nonpolar covalent bond. Think of a couple examples, write them down. I'm going to give you 3. Chlorine and chlorine, oxygen and oxygen, and nitrogen and nitrogen. You could pick just about any nonmetal that, at least any of the diatomics. If it is the same element bonding with another atom of the same element, there is zero difference between their electronegativity. Since there's no difference between the electronegativity, they will be sharing those electrons exactly evenly. Now, polar covalent bond be something like H and O, or C and O, or H and Cl. If you'll recall, if we have two nonmetals, which most of the nonmetals are on the right side of the staircase. If you have two nonmetals that are bonding, we know that's a covalent bond. Don't forget hydrogen is also a nonmetal. But a polar covalent bond is two nonmetals that have different electronegativities. So hydrogen has 2.1, chlorine, or hydrogen and oxygen, I'm sorry. Oxygen has 3.5, so there's a difference between those two numbers. You could do the same thing. Carbon and oxygen, there's a difference between those numbers. And then we have hydrogen and chlorine. There's a difference, so that makes it polar covalent. Now, if there's a really big difference, that would be an ionic bond. Think of some examples of an ionic bond. Well, any metal and nonmetal, so potassium and chlorine. K is way over here at 0.8. Chlorine is 3.0. There's a big difference between their electronegativities. And then Fe and O. Fe is right in here, 1.8. O has 3.5. Pretty big difference. Then we have aluminum and chlorine. Al, 1.5. Cl, 3.0. So big enough difference we can say that is a ionic bond. Now we've got some examples. Use the electronegativity values to explain why the FF bond is nonpolar and the HF bond is polar. So why is the FF bond nonpolar and the HF bond is polar? See if you can think about that. I'm going to go through the answer now. In the FF bond, there is no electronegativity difference. They have the exact same electronegativity, so electrons are shared exactly equally. So FF is nonpolar in F2. In the HF bond, there's a difference in electronegativity, so the electrons are not shared equally. Therefore, the HF bond is a polar bond. All right, so another way that we can look at this is by labeling these with a partial positive or partial negative charge. Each of the following bonds is polar. We want to use the periodic trends in electronegativity to label each atom in the bond with a partial positive charge, shown by this delta plus, or a partial negative charge showed by lowercase delta minus. So the H and O bond, which one is more negative, hydrogen or oxygen? Oxygen is more negative. It's got a higher electronegativity. Hydrogen has a lower one, so we have the delta positive on the hydrogen, delta negative on the oxygen. With nitrogen and carbon, nitrogen has a greater electronegativity. Carbon has a lower electronegativity. Remember, if it has a greater electronegativity, that's where the electrons are going to go. So we'll have a partial negative charge on the one with a greater electronegativity. So that's why we have a partial negative on nitrogen. Between iodine and fluorine, iodine is right here. Fluorine is right here. Fluorine has a greater electronegativity. So we'll have a partial positive on iodine and a partial negative on fluorine. Then we get silicon and bromine. Silicon is 1.8. Bromine is 2.8. So silicon is partial positive. Bromine is partial negative. We have chlorine and arsenic. I see arsenic is 2.1 and chlorine is 3.0. Looks like chlorine is more negative and arsenic is more positive. All right. The greater the difference in electronegativity between the two atoms, the more polar the bond is. So if there's a very big difference in the electronegativity, it's a very polar bond. To denote the charge separation in a polar bond, we're going to use an arrow with a crossed end. This is just another way of showing which side is positive, which side is negative. This arrow always points toward the atom that has the higher electronegativity value. I also like to look at the end over here and notice that it looks like a plus sign to me. That helps me to remember that is on the positive side and this is on the negative side. But remember it however you need to. So let's go ahead and label these. They're the exact same bonds that we had on the last page. Go ahead and label these with a crossed arrow. The arrow points toward oxygen, which is more electronegative, towards nitrogen, because it's more electronegative, towards fluorine in this case, towards bromine, and then finally towards chlorine in the last one. Alright, I'm going to go ahead and pause the video now, take a short break. We'll come back and finish up the notes after that.